Hello everyone, I'm Sajjad Montazeri and here we are with another tutorial on Grasshopper. Let's dive right in. Alright, to begin I will use interpolate curve in Rhino. I activate the snap tool and start drawing a curve like this, continuing it to this point. Then I extend it further to this point. Next I draw its mirror image on the right side, extending it to this part. I press enter to confirm the shape. Now I go to the lines section and draw a line like this, like this. Switching it to the perspective view, I select the line and move it upward using gumball tools. At this stage, I want to create a volume between these two curves. I can either select both curves here and use the loft command or proceed with Grasshopper for more pragmatic control. So I open Grasshopper, press Control and add a curve component to the workspace. Then I make a copy of the curve component. As you can see, I duplicate the curve component. Then right-click on the first component, select Set One Curve and assign it to the lower group. Then again, select Set One Curve and assign it here to upper curve. I can use the Loft component to create a surface between these two. I hold down Shift and assign the second curve to it as well. Make sure to check the output with a panel at this stage to ensure it is an untrimmed surface. You will get an untrimmed surface only if you've used the exact tools I mentioned. If you used our tools, your output will be prep and you won't be able to proceed with the rest of the algorithm. All right, now I extract a surface from it. So I bring in a surface component and connect the loft output to the surface input. Next, I want to divide the surface into sections. So I use an isotrim component. So I type it here and I use isotrim like this. I connect surface input to it. This I connect it. You could also scheme the surface component and directly apply loft as an input to isotrim. In the domain section, I can use a divide domain square component. So I bring divide component and apply divide domain square to this section like this. Now this requires a domain as well as uCount and vCount values. To define the domain, I use a construct domain square component. So I add it and apply it to the domain section, just like this. By default, construct domain square has umin, umax, vmin, and vmax, which vary between 0 and 1. To ensure that the surface starts from 0 and ends at 1, I need to right-click on the surface input and select Reparameterize. This allows us to see the divisions correctly. Now I extend the algorithm slightly. I can assign 4 sliders, each ranging from 0 to 1 to umin, umax, vmin, and vmax. So I use let's say 0.25 values and make 4 copies of it. As you can see, I arrange this component neatly. Right at the beginning, I connect the first one to umin, the second one to umax, the third one to vmin, and the last one to vmax. Now I can assign different values. For example, I set this one from 0 to 1, and for the other one, I define its range from one section to another. We do this because the exercise we are working on might not need to cover the entire surface. This way, you can easily control which areas are included. You can also experiment with different values and adjust the effect in different direction. I make them a little bit tidy again to ensure the entire surface is covered. The subdivision you see in this section are controlled by uCount and vCount. Here I can assign custom values as well. For instance, I type 50, make copy, so here I make a copy and adjust its value to 9 or 10 in one direction. Then I connect one to uCount and the other one to vCount to create a brick-like pattern on the surface. You can control as many segments as you need based on the height. You can perform some calculations to determine how many bricks fit in this section. For example, 30 by 10 seems to be a good idea. Now I want to extrude this. So I use the extrude component, I type it like this and bring it. I connect the surface to the base and specify a direction. I set the direction along the y-axis by typing y and then applying it to this part. Now the volume is defined, but as you can see, the thickness is very small. You can easily control the thickness with a number slider. For instance, I type 1.25 and I can adjust it in any direction I want. I increase the value, but since there are many segments, we need to wait a little bit. As you can see, the thickness is applied, but it might be in a direction that is not ideal for our design. Here I can use a custom preview to display this more clearly. So I bring it, apply the custom preview here and assign a material using, let's say, color swatch by typing it. I add the color swatch, connect it to the material, and now the visualization should be clearer. We can also use different color tones like this. For example, I select this one for now. It seems pretty beautiful. All right. If I increase this number, for instance, setting it from 6 to 9, it extends the thickness toward the back. If you want the extrusion to happen in the opposite direction, you can simply use a reverse component. I bring in the reverse component, connect it to vector unit, and it flips the direction. Now, if I change the value back to 6, the thickness will extend forward. Mhm, which is what we want in this example. This can now serve as an entrance wall for a building designed using metric bricks. The point here is we want to develop this further so that the Y unit input isn't just a single number. To do so, I want to apply a series of values. So I'll start the series with a custom number. For example, let's say 0.05 can be a good idea, and set it as the start value. The step size is 1 by default, and I'll keep it in that way. Now the count should be the product of the number of bricks in the U and V direction, meaning U count duplicate V count should determine how many values we generate for extrusion. So I bring in a multiplication component, connect U count and V count, and use the result as the series count. You can see the overall result as a count in the panel, like this. Now the generated values serve as the factor for extrusion, creating a three-dimensional step effect, like this. If you feel the values are too large, you can adjust the step size to control the variation. For example, let's say I use a step size of 0.01 and apply it to the step input to see the result. With this setting, you can see that the bottom, the extrusion is very small, and as we move upward, the extrusion increase. I could also try other values. For instance, I set to 0.25, apply it to the step, and observe the result. If I reduce the value a bit more, you can see even more interesting result. So I'll set this step size to 0.05 and remove the previous value. Now, another thing we can do here is to remap all these numbers. So I'll use a remap number component by typing it, taking the input values from this section. For the source domain, I'll use a bounds component to extract the minimum and maximum values from this set and correct it. The target domain is set by default between 0 and 1, and we can use different types of number as we like. For instance, here I use, let's say, 1 to 5, and after that I connect it as a panel format. Now I'll connect these remapped numbers to the unit and we can see the final result in this form. If we want to make things a bit more complex, we can add a graph mapper before connecting it to the factor input. I'll pass the remapped value through the graph mapper, then connect it output to the extrusion factor, I right-click on the graph mapper and select the sync function to observe the result. If the effect seems too weak, we can amplify it using a multiplication component. So here I type X, then connect the graph mapper, output to input A, and set B, let's say 1.25, to slightly exaggerate the values like this. So here I can change this value so easily and it will be more dramatic effect. I right click again and try some other graph types to explore different variation. For example, I can test the purling function which creates a pattern break effect like this. I right click again and try the sine function which generates a wave-like parametric wall. It also looks interesting. The point is I want another suitable way. So I switch back to purling. This is one way to create parametric walls, but there are other techniques too. For example, a tractor point. To do this, I'll take the surface output since each break is an individual surface and apply an area component by writing area here and to extract their centroids. Now I'll place a point manual to the in the top view for better control. So here we have top view, and then I'll switch back to perspective view, select the point, and use the point component in the Grasshopper. By right-clicking and selecting one point, I can introduce this point into Grasshopper environment. Next, I want to calculate the distance. So for that, I bring the distance component and connect point A and center it to point B. Now I have a set of distances which I can use as an input for remapping, and here I want to move these components forward a bit and to make it a little bit smoother. And instead of using the series, I'll connect distance to the input for remap number. And of course, I'll also use bounds from the same section as an input. Now we can see how the pattern dynamically adjusts based on the point's position. If I select and move the point, the algorithm reacts in real time, creating different effects. Let me raise it up a bit and we can better observe the result and then bring it back down. To further enhance the visualization, I can add a gradient. How? Just by writing it. I'll set the graph mapper output as the input for gradient parameters and right click to change the gradient type for a smoother effect, like this. Right click. I can adjust the gradient like this and apply it to the material, allowing us to see the final color effect. Now I'll select all the components, right click and hide the preview so we can focus only on the final result. If I switch to the render mode, we'll get a beautifully distributed parametric grid pattern with a randomized look. By tweaking the divide domain square, you can get different creative results. For example, you can create square panels instead of bricks, make smaller, finer bricks, rotate them vertically, experiment with various patterns and designs. All right, that is the end of our tutorial. I hope you've enjoyed. I will see you next time. Bye.